Our guest lecturer, Dr. Francesco Parisse, who is a researcher at the University of Genoa and got a PhD in civil engineering from the University of Minho. We are very honored at Diana FEA to have Francesco as a guest lecturer today, and is going to present some of the work he has done on the unreinforced masonry structures using Diana, which is of course a plus for us. So having said that, let's welcome Francesco. And Francesco, if you unmute yourself, basically the stage is yours.
Thank you very much, Jean-Claude, and good afternoon to all the audience. I want to thank you also, Diana Software House, for inviting me to present some of the results of my work during the PhD. And having said that, I will just go directly to the main content of the presentation. So first of all, I want to show you a presentation of myself, of my research in particular. My research field is the seismic assessment of reinforced masonry structures, as also Jean-Claude said. And by using numerical simulation with two different modeling approaches, basically finite element models and equivalent frame models, of course in Diana software and Tremori software. The results that I will show you today, they are associated to a benchmarking project funded by the Italian Department of Civil Protection and ReLUIS network in 2022-2023. And it is basically the benchmarking of different modeling approaches and software for the code-based seismic assessment of URM buildings, in which I was involved during my PhD thesis under the supervision of Dr. Rui Marquez, Professor Serena Cattari from the University of Genoa, and Professor Paolo Lorenzo from the University of Minho. Right now, I'm currently working on a different project, Newton, which is basically aimed at computing the seismic demand on non-structural components. And in this project, there is also an experimental part, in particular a shake table test on a reduced scale 3-story brick masonry building. In any case, if you have questions or you want to ask me something, feel free to send me an email to the address that is here. So moving directly to the outline of the presentation. Today we will go through a brief introduction and research framework of the ReLUIS project, but then we will talk about the key lessons that we learned from the benchmarking of different modeling approaches. So not only in Diana, but also in other finite element models. And this core part of the presentation is divided into different parts. The harmonized recommendation for seismic simulations, and with the pier response calibration and an example and limitation of this calibration. Then the procedure for results interpretation with two proposals, basically a graphical control method with band domains at the pier scale and a multicriteria approach to define the near collapse limit state. So let's start with the presentation. During my literature review in the PhD thesis, I found out that most of the relevant experiences in benchmark test and blind prediction highlighted a very significant dispersion of results when simulating the seismic response of reinforced masonry structures. As you can see from the coefficient of variation that refers to the peak ground acceleration associated to the ultimate displacement capacity in the benchmark test by Magenes, Lorenzo, and Cattari, or in the coefficient of variation of the ultimate displacement predicted during the blind prediction test for the Serra Ames project by Tomic et al. but these very large dispersions were also due to the fact that in the first two exercises, let's say, the participants were free to choose not only the modeling approach, but also the assumption. And in the case of the benchmark tests, in the first benchmark test, participants choose also the analysis method and the assessment procedure, while the framework in which the coefficient of variation are the smallest is the third benchmark test for the 2014-18 and 2019-21 ReLUIS project, again funded by the Department of Civil Protection from Italy, in which participants were only free to choose the modeling approach, and while the assumptions were initially defined by the organizers. And this is also helpful when we have to understand the differences between the results. So we will continue the research in this framework, in the framework of the benchmark test by ReLUIS, and in particular for task 3 of the project in 2022-2024, the main objective was to compare different modeling approaches and software for the code-based seismic assessment of masonry buildings. And the coordinators, of course, were Professor Serena Cattari from the University of Genoa and Guido Malgenes, but many different universities joined this project, mostly Italian university, but also the University of Minho, in which I was affiliated during the PhD work. And these universities were grouped into 6 research macro groups that performed the analysis. It's important to say that many of the results of the ReLUIS project related to the 2019-2021 project are published in the Bulletin of Earthquake Engineering, while the most updated results, so including also the results for the project in 2022-2024, are published in this book on the right, which is written in Italian, but we are also submitting some journal papers that will be published very soon in some international journals, and that are indicated during the presentation. The main objective of this presentation today is to present the key lessons learned from the benchmark test in the ReLUIS project, because we want to decrease the dispersion of results by providing consensus-based warning recommendation that tries to complement those recommendations that we have in building codes, and also providing control procedure. And we want to increase user awareness on the results by providing methods for results interpretation and reference range of response for benchmark structures that were analyzed. So moving to the research framework, we should say that the numerical simulations that were performed are pushover analysis, in which only the uniform load pattern proportional to mass is considered, and the seismic load is applied at the floor level for comparing purposes between the two modeling approaches that we consider. Of course, the main output is the capacity curve, but we also asked to the different participant university additional outputs in terms of damage pattern and internal forces and drift evolutions. So the modeling approaches that were considered are the finite element models and equivalent frame models. In the left models, we have many user assumptions to be made, but the results and these models have a good compromise between accuracy and applicability. While in equivalent frame models, we have fewer user assumptions, but the results are on the safe side, and they are very applicable in, they're mostly applicable in applied in practice. And of course, in my case, I used Diana for the finite element model and Tremuri for the equivalent frame one. But due to the participation to the ReLUIS project, I was also able to compare my results with the one from other software, in particular STKO, so the toolkit for OpenSeas, Abacus for the finite element models, and ProSum and 3D Macro for the equivalent frame approach. Moving directly to the features of the material models that were used in the FE models, we should say that the model in Diana and in Abacus consider a macro model with isotropic material models. In Diana, we use the total strain crack model, while in Abacus is used the concrete damage plasticity model. And they both simulate the same failure modes, such as tensile cracking and compressive crushing. While in STKO, the modeling strategy was a micro modeling with an orthotropic damage plasticity model, which can simulate opening and sliding of mortar joints and compressive crushing. But if we mostly focus on the total strain crack model in Diana, as you may know, this model was developed along the lines of the modified compression field theory by Vecchio and Collins in 1986, with its 3D extension by Selby and Vecchio in 1993. It is based on a smear cracking approach, and it is an hypoelastic model with second unloading. Moving to the user option that I selected for the total strain crack model, first of all, the stress strain concept is coaxial rotating, which means that the stress strain relationship are defined in the principal direction of the strain vector. And cracking occurs when the maximum principal stress exceeds the tensile strength. And it's the orientation of the cracks is always orthogonal to the maximum principal strain. Regarding the tensile behavior, I selected the exponential relationship, which is shaped by the fracture energy value and the crack bandwidth defined by Rotz in 1988. Also, the Poisson effect after cracking was activated, a reduction of the Poisson effect after cracking was activated. In terms of compressive behavior, I selected the parabolic relationship, and another important option, which is the compressive behavior with lateral cracking, which was selected the model by Vecchio and Collins in 1993. Regarding the equivalent frame models, we should say that the main difference between the three software and modeling approaches is the fact that in Tremuri and ProSum we have a lumped plasticity approach with 2-node beam elements, while in 3D Macro we have a spring-based approach with plain macro elements. The equivalent frame discretization is perfectly respected in Tremuri and ProSum, so with deformable and undeformable portion, while in 3D Macro there are no rigid portion. And another characteristic of 3D Macro is that mixed failure modes can be also simulated. The benchmark structures that we considered are walls, reinforced masonry walls that were idealized from internal walls from existing masonry structures. In particular, Pietro Capuzzi's school in Visso in Italy, the town hall in Pizzoli, again in Italy, and from a residential building in Aquila, Italy. So basically they are representative of the central Italy building stock. These are the front views of the unreinforced masonry walls, and in particular the 8 configurations were idealized from that were considered for the analysis in the ReLUIS project, from with different levels of opening layout irregularity. So basically the configuration, the wall configuration 1, 0 and 2, 0 are the most regular one, while going to the configuration tree, the opening layout irregularities increase. Also because one of the objectives of the ReLUIS project was to benchmark different criteria for the piers effective height definition in EF model, with different criteria by Dolce in 1991, Ogenti 2004, and Lagomarsino et al. In 2013. Regarding the piers, the following configuration were considered, in particular a slender pier with a fixed free boundary condition, 2 squared piers with a fixed free and fixed boundary condition, and the squat pier. Let's go to let's present the key lesson from this very large research work, starting from the harmonized recommendation for a seismic simulation. But before starting, I want to highlight that we found out a high sensitivity of prediction to material model parameters. And just to give you an example of these sensitivity of results, here I want to present the numerical simulation of the pier response that you can see in the picture with the total strain crack model in Diana, by activating or not the compressive reduction, the compressive strength reduction with lateral cracking by Vecchio and Collins. So if this reduction is active, then we have the red solid line. If this is not active, then we have the dotted line. So as you can see, we have some differences in terms of shear force and displacement capacity, but which is the most reliable the most reliable prediction? Well, as engineers, what we can do is to check the shear stress distribution at the midsection of the pier. And in this case, we can easily see that the model in which the reduction by Vecchio and Collins is active is more representative of the physical behavior of masonry, because in correspondence of the midpoint of the cross section, we have a drop in shear stresses due to the cracking of masonry, in which is not possible the shear stress transfer. So we could have reached so just to say that when using advanced approaches, high user expertise on the approach and knowledge on the material behavior are required to obtain reliable results. In any case, we could have reached the same conclusions if the numerical response was compared with an experimental response, so this gray envelope by Majanes et al. Another example that I want to present you that shows the sensitivity of the prediction is the one always related to the pier response calibration by Daltrey et al. In 2021 that was developed during the previous ReLUIS project, in which even if the pier response was calibrated in terms of strength, stiffness, and also, as you can see, the damage among all the models were quite similar. If we look at the curves, there is a very large dispersion in terms of drifts. So this is again to say that the predicted response of masonry material needs to be initially calibrated and eventually checked. But which is the scale for this calibration? It is the pier scale. Why? Because we don't have any reference at the wall and building scales, because of the availability of experimental results for model validation, and because the pier scale allows also to compare the results from different modeling approaches, and it is used for seismic assessment through code-based capacity models. So If we want to explain which could be the main steps for the pier response calibration, we will see in the following slides that we start from defining which is our modeling approach. Then we identify which is the masonry type that we want to analyze, and in this case we selected a stone masonry with the mechanical properties that you can see in the table, which were derived from the 2019 Italian commentary with a knowledge level 2. Then we have to define a target response, and in this case the target response is not an experimental campaign, but the code-based capacity model in terms of shear resistance and drift capacity. This is due for the practice-oriented view of the ReLUIS project. And in particular, the shear resistance is a function of the dominant failure mechanism, the geometry of the pier, the mechanical properties, and the axial load ratio, while the drift capacity is a function of the dominant failure mechanism and also axial load ratio in the most updated codes. So if we selected the stone masonry, we know that the capacity model for code-based assessment will be the flexural mechanism and the diagonal cracking mechanism, in which we have the simplified expression for the shear resistance, and then we have also the drift. But the pier response calibration needs also the selection of representative piers. So if we have a benchmark structure that we have to investigate, we should select and identify the piers aspect ratio and load ratio. Typically, this identification is done a posteriori in finite element models, and is done for verification purposes, while in equivalent frame models is done a priori because of the intrinsic equivalent frame idealization. But so our recommendation is to identify a priori the piers geometry and the load ratio also in finite element models to compare the response of specific representative piers with the ones from code-based capacity models. But which are representative piers? Piers are considered representative in our view if the aspect ratio, load ratio, and boundary condition are relatively recurrent in the wall under investigation. Alternatively, also standard piers with features similar to the ones assumed in the formulation of the code-based capacity models can also be selected. An example of this pier calibration is shown in the following. So we started with this pier response of the slender pier with a fixed free configuration that you can see on the left. We defined which were for each material model the main parameters that govern the post-peak response that you can see here. So basically the fracture energy values in the total strain crack model in Diana and in the damage plasticity micro model, plus the compressive strength reduction factor in Diana and the latency parameter for the damage plasticity micro model. While in the concrete damage plasticity, the drift mainly depends on the strains at the residual strength. And after calibrating these properties, the final pier responses predicted by the three different finite element models are the following ones. So as you can see, the dispersion in terms of drift reduced significantly, as well as the one in terms of shear force. And using the new set of material properties didn't change significantly the shear strength, as you can see from the comparison with the code-based models in terms of flexural domain, and didn't change significantly also the damage pattern predicted by the three different models, except for the first the first model that here we can see on the left. But we should say that there are some limitations on the selection of representative piers, because no set of material properties allows simulating the code-based response of a set of different piers. And this is very clear if we compare the results from two different piers, so a squared pier and a slender pier that we saw before. Basically, the drift capacity, the code-based drift capacity cannot be captured by the red curve by Finite model 2. And so there is still some dispersion of results, of course. Although in terms of damage pattern, the results are quite consistent among all the three different finite element models. So the recommendation is to select a limited set of representative piers for the pier response calibration. Moreover, there are also some limitations on the target response, because the code-based capacity models assumed simplified hypotheses for simulating the behavior of masonry piers. For example, we have the assumption in the Turcek-Kakovic 1971 diagonal cracking strength domain that the horizontal stresses in the central point of the pier are negligible, are zero, or the fact that there is no transition between different drift capacity associated with different failure mechanism. So just to say that the finite element prediction can be actually different from the code-based capacity response if these differences are properly justified. And just to confirm this, I want to show you some results from the sensitivity analysis for the squat pier that I performed in Diana by using the rotating versus the fixed stress strain concept. In particular, as you can see from the shear shear strength domain, when using the total strain crack model with the rotating approach, so the cross marker, the shear strength is much higher than the diagonal cracking shear domain by Turcek-Kakovic, while when using the fixed approach, the prediction are actually consistent with the diagonal cracking shear domain. But which is the correct prediction? Actually, again, we analyzed the horizontal stress distribution in the midsection of the squat pier, and we saw that in case of the rotating approach, the horizontal stresses in the midsection of the pier are not negligible at all. So this is the reason why we have also this increasing of shear stress, strength in our model. While if the hypothesis of horizontal stress limited in the cross section of the pier, if this hypothesis is respected, then we also have a consistency with the diagonal cracking shear domain by Turcek-Kakovic. But in any case, we don't know if this domain is still valid for piers aspect ratio smaller than 0.67, as it is in our case. So we need some reference experimental response for squat pier for validating the finite element prediction and also the code-based capacity models. Moving to the procedures for results interpretation, from the pushover analysis on the benchmark walls, we have to say that even with the pier response calibration, we can have non-negligible dispersion at the wall scale among different modeling, despite the fact that the damage patterns are quite consistent between all the three finite element models. But if we check again in the pushover curves, we can see some differences in terms of base shear force and in terms of displacement capacity. But if we again perform some checks at the pier scale, so we analyze basically the squat pier at the base of the wall, which mostly control the response of the pier, we can see that it's this pier that behaves differently between the three models. So we could explain the differences of the pushover curves. And our recommendation is to check the response of significant piers with the code-based capacity models after performing the analysis by using the control method with band domains that you can see here and that I will explain you in the following slide. Basically, this method is a graphical method. It's defined again at the pier scale and consider the epistemic uncertainty from the software to software variability on the pier initial axial load and zero, which is so this uncertainty is called delta 1 and can be also assumed equal between 5 and 10% of N0. And then this method consider also the variation of the pier's axial load during the analysis, which is delta 2, and can be estimated by the software or alternatively assumed as 10 to 25% of N0, depending on the position of the pier, if it is an internal pier or an external one. After this, we can easily define which is our bands in our band in terms of element shear force. So this is our expected shear force in the pier, and then we can compare. We can calculate also the vertical band in terms of drifts, always starting from the variation of the axial load during the analysis, and compare the results of the different finite element models and equivalent frame models all together. Or this method can be also effective to indirectly control the results from one user and one software with the one from multiple users and multiple softwares. Another remarks that was evidenced during the pushover analysis is the fact that sometimes the pushover curves by finite element models have some a reduced base shear drop, so we cannot even after the exceedance of the pier's drift threshold. In particular, as you can see from the blue and black curve, here we don't have a significant drops in terms of base shear coefficient, even though the drifts associated to the squat pier at the base that controls the response of this wall exceed the code-based threshold values of 0.5% for the diagonal cracking failure. So our suggestion is to basically define a posteriori the points in which the analysis should be considered stopped, and to consider a multi-level approach to define the near collapse limit state. So with checks not only at the global scale but also at the local scale, basically at pier scale, with exceedance of drift threshold in piers loaded with higher 20% of the base shear force. Moreover, during the analysis, we also found out that there could be some violation of the balance of vertical forces. Although again, the damage pattern predicted by the different models is quite consistent between the finite element models that were considered in the project, but still the pushover curves can be different, as you can see from the graph. And when checking the percentage variation in the vertical reaction during the analysis, you can see that in some cases this percentage variation starts to increase a lot, and if it is higher than 1%, we actually stop the analysis and fixed our near collapse limit state at this point. So for this reason, we proposed also a multi-criteria approach to define the near collapse limit states that consider also this additional check on the variation of vertical force during the analysis. And when we, so just to show you which can be the possible impact of this multi-criteria approach to the prediction from finite element models, these are the initial variations that were estimated by the different finite element models for all the configurations that were analyzed. And if we apply the multi-criteria approach, as you can see, the dispersion, the variation of results reduces a lot in terms not only of maximum and minimum value, but also in terms of values within the Q1 and Q3 quartiles. Moving directly to the final remarks, here I want to highlight that there is still a residual dispersion of the bilinear pushover parameters between finite element models and also in their comparison with equivalent frame models. But these coefficients of variation are limited in terms of secant stiffness and base shear coefficient, so they are basically limited and their values are smaller than 20%. While the dispersion is still high in terms of displacement capacity. And this is high not only in when considering finite element models only, but also in equivalent frame models only, and in the comparison between the two of them. So we still have to make some progresses in research to reduce this dispersion in the ultimate displacement. Although there is a moderate to good agreement in terms of damage pattern, as we saw during the presentation, and we can also see in these slides for this agreement was found for all the work configurations. Moving to the final remarks, so we want to highlight that there is required a high user expertise and knowledge to obtain reliable results. The pier-scale is the reference scale for comparing the prediction from different modeling approaches and also to check results after the analysis with the proposed graphical control method with band domains. We need a drift definition that consider not only the failure mechanism, but also other factors such as the axial load, masonry type, and so on. And we need a multi-criteria approach to define the near collapse limit state, so not only multi-level. I want to add also some final thoughts and future work. Because we, as I mentioned before, additional research is needed to simulate the response of URM structures using finite element models, but I would say any model. And masonry-specific models, in particular the engineering masonry model in Diana, could be adopted along with the total strain crack model for my research, for example. And specific models could be implemented to easily visualize the response of standard piers from, for example, static or cyclic analysis for given set of material properties, and also in the post-processing of results to perform control procedures that we propose in this webinar. I want to finally acknowledge Diana for the invitation in the webinar, and my research R&D unit, Institute for Sustainability and Innovation in Structural Engineering, is from Portugal, in which I was associated during my PhD work, and the Portuguese Foundation for Science and Technology, which funded my research. And of course, all the researchers, all the university that work with me during the ReLUIS project, funded by the Italian Department of Civil Protection. Thank you very much, and I will be very glad to answer your questions. Thanks.
Thank you very much, Francesco, for this very nice presentation. And I must say that the amount of work that have been done is quite impressive. So thank you for trying to summarize this in this presentation. There was just a question, but I think you basically answer it on the last slide. Basically, the question was: have you considered to use engineering masonry model in Diana? But basically, this would be the next step. I would say, based on your conclusion, isn't it?
Yes, of course. I will try also to consider it in the future for also because it simulates all the failure mechanism of the masonry. Of course, it is mostly developed for regular masonry, but I think it can be used also for other types of masonry. I mean,
yeah, this could be an interesting next step, I would say.
Yes.
Let me see if there are more questions that can be of interest. There is a question: can you refer to a document where the drift limits are described? Do you have any reference document for that?
For the drift limit, yes, I referred not only to the Eurocode, but also to the Swiss code, in which there is a formulation that consider also the axial load variation, so in which the drift is a function of the axial load. This is actually implemented also in the updated Italian code, but this, let's say, this new equation can be used only in the flexural resistance and not only in the diagonal cracking resistance, while in the Swiss code there is no such difference, and the drift associated to each failure mechanism can be modified based on the axial load on the pier. So regardless of the failure mechanism, basically. Okay, thank you. And there are a couple of attendees who are asking if they can send you email directly to of course,
discuss
I would be very glad to answer them if it is possible. Of course, yes. And among the few questions, there's a lot of compliments that I need to share about the quality of your work and this nice presentation. So I would say that I will speak in the name of the audience. We want to say a big thanks to you, Francesco, for taking the time to present this extensive work that you have done. And it was really a pleasure to have you as a guest lecturer in our technical webinar today. So I want to thank you under the name of Diana FEA, but also for the audience, the large audience that were there today during this webinar. Thank you for your time and the quality of your presentation. Really appreciated, Francesco. Thank you very much, Jean-Claude, and thank you very much to the audience for attending it.